Hi everyone, thanks for tuning in. My name is David Weitz, and today I'd like to tell you about rounding dynamic matchings against an adaptive adversary. By the end of this talk, you should be familiar with the dynamic matching problem, the notion of adaptive adversaries, and what I mean by rounding in this context. So let's get to it. In dynamic graph algorithms, the input is an n-node graph, G, initially empty, and at each time step, we have an edge update. An edge is either added or removed from the graph. We'll denote by gt the graph G at time t, and so what we have here is G0, this is G1, G2, G3, G4, and so on and so forth. And throughout, our objective will be to maintain some good solution to a graph theoretic problem, and we'd like to update it fast in the face of these edge updates. And by fast, I mean in particular, significantly faster than the naive solution, which would recompute a solution from scratch. Ideally, we'd even like polylogarithmic update, or even constant if possible. Focusing on the problem we consider in this paper, the dynamic matching problem. Here, the task is to maintain a matching M of small approximation ratio, where as usual, the approximation ratio is the maximum overall graphs and time steps of the max matching at time t, which we denote by mu of gt, to the size of the matching we maintain. If you strawman solution, we can easily maintain a one approximate solution in update time, which is linear in the number of edges, or a two approximation in a time which is linear in the number of nodes. And as it turns out, we now know a large number of algorithms which do significantly better. I won't have time to discuss all of these prior works, but let me just give you the executive summary for now and elaborate a little bit more later. So to date, among dynamic matching algorithms, randomized algorithms are significantly faster than their deterministic counterparts. However, all of these randomized algorithms need one crucial assumption for their analysis and for their guarantees to hold: the oblivious adversary assumption. Now, whether or not you've seen this definition before, this is a great opportunity for me to tell you about the distinction between oblivious and adaptive adversaries. All right, so in the dynamic algorithms literature, we distinguish between two types of adversaries. The first is the oblivious adversary, which you mentioned in the previous slide, which this adversary determines its update sequence in advance based on the algorithm, but not based on the algorithm's random coin tosses so far. The second, much more powerful adversary is the adaptive adversary, which determines its update sequence in an adaptive fashion based on the algorithm's execution so far. And in particular, based on the algorithm's randomness so far, based on its random coin tosses. Now, you might wonder why you should care about this distinction other than good old-fashioned paranoia, but as it turns out, there's a really good reason to care about this distinction, even if you don't particularly care about dynamic algorithms. And this motivation was pointed out by Madri some 10 years ago in the context of speeding up static algorithms. Let me elaborate on this point a little bit. So for a lot of problems, our method of choice to solve these problems goes via Turing reductions or Cook reductions. So here we solve some problem A by solving several instances of some problem B, assuming oracle access to a solver for problem B. So pictorially, it looks something like this. We have an algorithm for problem A, and along the way, it will solve some instances of problem B, B1, B2, B3, and so on and so forth. Now, given a static algorithm for problem B, this will give us an algorithm for problem A. However, in a lot of these reductions, these subsequent BI instances are similar to each other. Okay, in particular, B1 is somewhat similar to B2, which is somewhat similar to B3, and so on and so forth. And in that case, recomputing a solution from scratch is wasteful. And there's a lot of speed gains which we can get by implementing all of this using a dynamic algorithm for problem B. So we'll use our dynamic algorithm for problem B to solve instance B1, then update the graph to move from B1 to B2, solve the problem on B2 with the dynamic algorithm, update the graph to get to B3, and so on and so forth. However, here we have to be careful, because in a lot of these reductions, these BIs depend on each other. And the general flow is as follows. We'll solve instance B1. Based on the output to this instance, we'll decide which next instance of B we want to solve, B2. Based on the solution for B2, we decide on the next instance, B3, and so on and so forth. And so what happens is that effectively, the updates that bring us from B1 to B2 depend on the behavior of the dynamic algorithm. And so our algorithm for problem A is effectively an adaptive adversary for the dynamic algorithm for problem B. And so if we want to speed up static algorithms using dynamic algorithms, we need our dynamic algorithms to work against adaptive adversaries. So this observation of Matri's has motivated a growing number of work on deterministic algorithms, deterministic dynamic algorithms, which trivially work against adaptive adversaries, as the definition of the algorithm tells you what the realization of the random coins are. There are no random coins. This has also motivated a growing number of work on randomized algorithms that, despite being randomized, still work against adaptive adversaries. Okay, let's tie this into the problem at hand, the dynamic matching problem. The state of the art for dynamic matching is that all randomized dynamic matching algorithms only work against oblivious adversaries, and the fastest such randomized algorithms give us the following guarantees. We know due to a result of Solomon how to get a 2 approximate matching in constant amortized time. And we know, due to a number of papers in recent years, how to get a slightly worse than 2 approximate matching in polylogarithmic worst case update time. And finally, due to a recent result in SODA this year, we know how to get slightly better than 2 approximate matching in arbitrarily small polynomial update time. Okay, that's the state of the art. What do we show in this work? Well, in this work, we give the first randomized dynamic matching algorithms, which work against adaptive adversaries. And these algorithms essentially match all the previous results from the previous slide, up to these small caveats marked in red. So to summarize, we essentially match all of the known results for randomized algorithms up to now, while doing without the oblivious adversary assumption. Great, so I hope by now I've piqued your interest and you're curious to find out how we got these results. So let's get to it. So our starting point for this work is the following observation, which I'll substantiate in a few more slides, that dynamic matching Sparsifiers help solve dynamic matching faster, better, stronger. Okay, motivated by this observation, what we show in this work is how to use fractional matching on the one hand and edge coloring on the other to obtain better dynamic Sparsifiers. All right, so this will serve as our roadmap for the rest of the talk. Here's the plan. In the next 5 minutes or so, I'll tell you about Sparsifiers and why you should care about them in the context of speeding up dynamic matching algorithms against adaptive adversaries. I'll then spend about 3 minutes motivating the study of fractional matchings in the context of Sparsifiers. And then I'll spend about 2 minutes talking about edge coloring. And then once we have all the pieces of the puzzle, I'll tell you about the general framework, how we combine all of these together to get all of our results. All right, so without further ado, let's talk about Sparsifiers. An alpha Sparsifier of graph G is a subgraph H with maximum matching size in H, mu of H, at least 1 over alpha times the max matching size in G, mu of G. Now, as the name might suggest, we'd like these graphs to be as sparse as possible. How sparse can they be? Well, by definition, an alpha Sparsifier H must have at least 1 over alpha times mu G edges. So there's a limit to how sparse these can be. In particular, any constant approximate Sparsifier must have size at least a constant times the max matching in G, mu of G. And in a couple of slides, I will convince you that this is what we want. This is the holy grail if we want to speed up dynamic matching. We want constant approximate Sparsifier of constant times mu of G size. But before that, let's take a quick detour through the following observation due to Gupta and Peng, that the matching problem is in some sense stable. And the observation is as follows. If M is an alpha approximate matching at time t, then after any small number of updates, in particular at most epsilon times the max matching size in GT, the matching M, or the undeleted edges of the matching M, remain an approximately or nearly alpha approximate matching, an alpha plus epsilon approximate matching. And the intuition here should be clear. After a small number of updates, opt cannot increase by much, and M cannot decrease by much. So we essentially still have an alpha approximate matching. Now notice I've boldened the word any here for any small number of updates. And in particular, this is true even for an adaptive adversary, even for a sequence of updates generated by an adaptive adversary. This is just a counting argument. It doesn't matter how the updates are generated. The matching will remain a good matching. Okay, so how do we combine this notion of stability with Sparsifiers from the previous slide to get fast dynamic matching algorithms? So the following lazy recomputation approach and meta theorem implied by the work of Gupta and Pang is as follows. If you have a dynamic algorithm A, which maintains alpha sparsifiers of size S using update time t, then there exists an alpha plus epsilon approximate matching algorithm A prime with update time t plus roughly S over the max matching size in G. And this algorithm is very simple. It's 2 lines, so let me go through it. First, in the background, maintain some sparsifier H. Remember that maintaining the sparsifier here takes time t, so that contributes a t factor here in the update time. And in addition, periodically, in particular every epsilon times mu of gt updates, we'll use a static algorithm to compute a 1 plus epsilon approximate matching in H in time linear in the matching size. Sorry, in time linear in the matching sparsifier size, so roughly S. So we're spending about S work every roughly mu of G steps, so this contributes this term over here. An amortized contribution to the update time. Now, why is this an alpha plus epsilon approximate matching algorithm? Well, remember that our sparsifier H is an alpha sparsifier. So maximum matching in this graph is an alpha approximate to the max matching in G. On the other hand, we compute a 1 plus epsilon approximate matching in H. So overall, we get an alpha plus alpha epsilon approximate matching. And by the stability property from the previous slide, during the following updates, we remain an alpha plus roughly epsilon approximate matching. Now, in particular, the second point bears emphasizing. If our dynamic sparsifier algorithm works against adaptive adversaries, so if step 1 works against adaptive adversaries, then so does the dynamic matching algorithm A prime, because step 2, as we mentioned in the previous slide, also works against adaptive adversaries. Great. So hopefully you see why you care about sparsifiers in the context of dynamic matching. Let me quickly summarize and show a few applications. So again, to summarize, given a dynamic alpha sparsifier of size S with update time t, we immediately get a dynamic alpha plus epsilon approximate matching with update time t plus roughly S over mu of G. And if the first algorithm works against adaptive adversaries, so does the second. So a few applications. In their work in 2013, Gupta and Pang gave a 1 sparsifier, so optimal approximation ratio, of size at most quadratic in the max matching size. So maybe quadratically off from what could be the optimal, with update time root n. Plugging this into the meta theorem above, they get a 1 plus epsilon approximate matching with update time roughly root n. What we're going to show in the rest of the talk is a 2 plus epsilon sparsifier. So we'll give something up on the approximation ratio, but with optimal size and optimal update time. Putting all of these together, we'll get a 2 plus epsilon approximate dynamic matching algorithm with optimal update time. So the remainder of the talk, I'll try and substantiate the bottom left 4 entries of this table. The first ingredient we're going to use for our sparsifiers are fractional matchings. And as a reminder, a fractional matching in a graph G is a vector X satisfying the fractional matching constraint. For every vertex V, sum of its incident edges X value is at most 1. And in particular, what we're going to use later is the fact that we can maintain such a good fractional matching X deterministically in polylog worst case update time. So in particular, we can do so in the face of an adaptive adversary. Now you might be wondering if we can just round these fractional matchings into an integral one, and maybe sample each edge with probability proportional to its X value and get a good matching. As it turns out, this is not true, but the next best thing is true. In particular, if we consider the fractional matching from the previous slide, then as we showed in Arar et al. 2 years ago, a random subgraph H, which samples each edge E with probability roughly XE, independently for every edge, is with high probability a 2 plus epsilon sparsifier of optimal size. So from this lemma, we find that the dynamic fractional matching from the previous slide gives us a static sparsifier. Sample every edge independently with this probability. Now the natural question is, can we maintain this in a dynamic setting? And so a little more precisely, can we make sure that we have a sample with each edge E appearing in the sample with probability XE log n independently while X undergoes changes due to updates to the graph? And as we showed, versus oblivious adversaries, this is very easy. If an edge E has its X value changed, just resample it. So pictorially, it looks something like this. We have our sparsifier at time t. The oblivious adversary, say, maybe adds an edge at time t plus 1. Notice that these are independent of each other by the oblivious adversary assumption. Now, our fractional matching algorithm updates our fractional matching, only changing a small number of x values. And then we just resample these x values. Since the edges that we resample are independent of the edges that we don't resample by the oblivious adversary assumption, all the edges are sampled independently. Unfortunately, for an adaptive adversary, this argument just goes out the window because now the update at time t plus 1 can depend on the sparsifier at time t. So it can depend on the random coin tosses of the algorithm so far. And so it seems that in order to resample versus an adaptive adversary, if we want the sparsifier h as above, we need to just resample every single edge. So this would require omega m work, and even if we spread this over periods of time, this would still give us m over n update time, which is too slow. Okay, so it seems that sampling independently is a non-starter. So let's sample edges in a dependent manner. And for that, we'll rely on the next piece of the puzzle, edge colorings. As a reminder, an edge coloring of a graph is an assignment of one of k possible colors to the edges of the graph, such that no two incident edges share a color. And if you're wondering how this relates to matchings, notice that every color is a matching. No vertex has two purple edges incident on it. So for example, the purple color class is a matching in the graph. Now it's trivial to edge color a graph using m colors, where m is the number of edges. Just assign a different color to each edge. But as it turns out, you can use significantly fewer colors due to a classic theorem of Vissing from over half a century ago. If G has max degree delta, then the minimum number of colors you need to edge color it is either delta or delta plus 1. And what we're going to use in a dynamic setting is the fact that you can maintain a 2 approximation to this, that is a 2 delta edge coloring, deterministically in log n worst case update time. So again, deterministic means, in particular, it works against an adaptive adversary. And we'll use this crucially later. All right, so we have all the pieces of the puzzle. Let's complete it. Let's see how we can use dynamic fractional matchings on the one hand and dynamic edge colorings on the other to obtain a better dynamic sparsifier. As a warm-up, let's start by showing how to instantiate this framework in a static setting using static fractional matchings and static edge colorings. So let's fix some fractional matching x. Given this fractional matching x, let's define the following logarithmic number of subgraphs. Gi is the subgraph induced by all edges that have x value roughly 1 over 1 plus epsilon to the I. As our first observation, we notice that each of these subgraphs, each of these subgraphs have maximum degree roughly 1 plus epsilon to the I, or roughly at most 1 plus epsilon to the I. And the proof is rather simple, so let's get to it. For every vertex v, by the fractional matching constraint, we know that 1 upper bounds the sum of the vertex v's incident edges, x values. And by restricting our attention to v's edges in gi, we find that the degree of v in gi times 1 over 1 plus epsilon to the I is at most 1. Multiplying through by 1 plus epsilon to the I, we get our observation. What we'll use later is the fact that we can 2 delta edge color a graph. So by adding some dummy colors, if the max degree is smaller than 1 plus epsilon to the I, we can maintain a 2 times 1 plus epsilon to the I edge coloring in each of these GIs. And we can even do so dynamically with worst case polylog update time versus an adaptive adversary. But again, let's stick to static sparsifiers for now. So we have our fractional matching, we have these GIs, and for each such GI, we have a 2 times 1 plus epsilon to the I edge coloring. Our following observation is that if we sample a subgraph H by taking a union of 2 log n colors from each of these GIs, sampled without repetition, then each edge E is sampled with probability exactly, well, up to 1 plus epsilons, xe times log n. Right? If E is in GI, we took 2 log n colors in GI, and each of these has a 1 over 2 to the 2 times 1 plus epsilon to the I chance of containing E. So since xe is 1 over 1 plus epsilon to the I, we get this equality. Okay, notice this should seem familiar. This is exactly the independent probability with which you wanted to sample for Ararata. Now, of course, these are not independent samples. Edges are not sampled independently. If two edges are in the same subgraph and share the same color, they're either sampled together or not sampled together. There's no chance that one is sampled and the other is not. So the question is, does this give as good a sparsifier as sampling independently? And the key lemma for this talk is that indeed, this is such a good sparsifier. So if we take H as in the previous slide to be a union of random subsets of 2 log n colors from each coloring CI, then H is a 2 plus epsilon sparsifier of optimal size, which can be sampled in optimal time. Remember, mu of G is the best size we could hope for, and if we want to write it, you need to spend that much time. So here's the proof of at least 2 of these claims. The bound on the size of H is rather direct. H is made up of 2 log n colors in 2 log n graphs, so log squared n many colors. As we said before, every color is a matching. So none of these colors consist of more than mu of G many edges by definition. So H is made up of at most mu of G times log squared n many edges. That's the first claim. As for sampling, notice that in order to decide which colors we want in H, we only make some polylog many random choices, and after that, we write H. So all in all, this takes O tilde times mu of G time. The approximation ratio turns out to be a little trickier to argue about due to the correlations. You're welcome to read the paper for more details or reach out if you want to hear more. I'm always happy to talk about this. Great. So far we've established how to combine static fractional matchings and static edge colorings to obtain static sparsifiers. How do we make this setting dynamic? Well, as it turns out, all we need to do is use dynamic algorithms for fractional matching and dynamic algorithms for edge coloring and just recompute periodically. In a little more detail, to maintain a 2 plus epsilon sparsifier H of optimal size dynamically, we'll do the following. In the background, we maintain a fractional matching and colorings in GIs as in the previous slides. Remember, we can do this dynamically in polylog worst case time versus an adaptive adversary. And then what we'll do, every epsilon mu GT updates, we sample H in O tilde of mu GT time. So this time adds another O tilde of 1 to the amortized update time. And notice that H is a 2 plus epsilon sparsifier at the beginning of the update. And by stability of the matching problem, it remains a 2 plus, say, 2 epsilon sparsifier until the end of a period. All in all, what we get from this is a 2 plus epsilon sparsifier of optimal size and optimal amortized update time, which we can maintain against an adaptive adversary. Now, if you remember from a good few slides ago, using the meta theorem of Gupta and Peng, what we get from this is a 2 plus epsilon dynamic matching algorithm with the O tilde of 1 update time. I'll spare you the details and not go over it again. Let me instead give you kind of the main takeaways from this talk. So what we show in this work is a new framework for dynamic sparsifiers, and by the meta theorem of Gupta and Peng, for dynamic matching. And we get these results by instantiating this framework with different dynamic algorithms for fractional matching on the one hand and edge coloring on the other. And from this, we obtain all of our quantitative results. Before sending you on your way, let me maybe mention a few intriguing open questions still remain. So first, most relevant to this work is the natural question, does this framework allow for more applications? Can we get new results? And as it turns out, from a as yet unpublished work of Bernstein et al., this framework can be used to obtain optimal approximation in bipartite graphs in a decremental setting. The natural question is whether or not we can find yet more applications. More generally, for the dynamic matching problem, it seems that we've hit something of a wall when it comes to randomized algorithms, or at least fast algorithms. We know how to obtain 2 and 2 plus epsilon approximations in polylog or even constant update time, but we don't know how to get anything better than 2 in polylog update time. So the natural question is, can we beat 2 in polylog or constant time? In fact, we don't even have any lower bounds to rule out 1 plus epsilon approximation in polylog or constant time. Can we do this, or can we show that it's impossible? And finally, generally, there's lots of exciting open problems in the area of dynamic algorithms. Possibly, I think the most appealing to me is dealing with adaptive adversaries. And there's been an increasing number of work on beating adaptive adversaries. I invite you to come and try and join the party. And with that, I'll thank you for your time and hopefully see you at Stock.